This week, we'll see how Elijah Graves Otis helped change the skyline of our cities. We'll see a paper mill and a 100-year-old invention that's just making it to the home now. Gee, this is the last show, and we still didn't get to see a cheese factory.
What if I told you that modern science would soon make it possible to have a light source in our homes that would eliminate shadows, be at least 6 times as efficient as the old 40-watt light bulb, and last 10 times as long? This magic light source makes use of a thing called single quantum photoabsorption, where atoms of a substance are raised to an excited state by the absorption of incident radiation and returned to their original state by re-emitting light. Sound a little fantastic? Well, modern science did invent this thing in 1867. The first practical one was constructed in 1939, and they've been overhead ever since. The fluorescent light gets its name from the coating on the inside of the tubing. Fluorescence is a phenomenon where certain substances will emit light when they're stimulated by other radiation. Invisible ultraviolet light's the biggie when it comes to the original stimulus. Some rocks found in nature fluoresce, and some laundry detergents leave tiny fluorescent particles in your clothes so that ultraviolet light from the sun will make them appear brighter. The television you're looking at right now uses fluorescent particles to display my handsome face, only there's no ultraviolet in the picture tube. The stimulus there is from a beam of electrons. A fluorescent light uses a mercury arc to provide the ultraviolet source. The tube is officially a low-pressure mercury discharge tube. High-pressure mercury arc lamps are used to light roads and stadiums, and another metal vapor arc lamp is also used for street lighting. Sodium vapor, the yellowish ones. The low-pressure mercury discharge tube mostly emits ultraviolet light, but that fluorescent coating changes that energy to visible light. The color of fluorescent light can be controlled by choosing different phosphors, and that's why these come in so many different flavors. The shadowless quality of the fixtures has nothing to do with the arc or the coating. It's just that tiny little light sources create shadows. And the big ones, like the sky on a cloudy day or a 3-foot fluorescent tube, don't. One of the reasons that these lights haven't simply taken over is that they require more parts. The mercury vapor arc is ionized gas. Lightning is also ionized gas. In the case of lightning, the gas is air. Unionized gas doesn't conduct electricity. It's a darn good thing in the case of air. Ionized gas not only conducts electrical current, it conducts more current as the current it's conducting increases. That would lead to a rapid destruction of the tube without this black lump. This is the ballast. In the old days, the ballast was just a big coil of wire. The arc was initiated by heating cathodes in the end of the tube. The cathodes are coated with a substance that readily gives off electrons when heated. A small starter would preheat those cathodes and then give the coil an electrical flick, like the points in a car ignition to a spark coil. The resulting spike of high voltage would cause the gas to ionize and conduct. As soon as the gas conducted, the ballast would then limit the current to a safe value, and the cathodes would continue to be heated by the arc itself. You still find this operation on a desk lamp that has a manual push-to-start switch. Holding the switch preheats the cathodes. Releasing it strikes the arc. This one's a demonstration lamp from General Electric. The fact that it's only coated halfway is the demonstration part. The dents in the bulb are a new design that gives the tube more surface area to emit light. Most fixtures now are the rapid start type. The ballast contains additional windings that heat the cathodes continuously, just a bit. This allows the lamp to start right away and run even more efficiently. Some ballasts aren't ballasts at all. This one's a high-frequency generator that excites the gas without really striking the arc. This type of system isn't as efficient, but it allows the tubes to be operated from low-voltage battery supplies. The fluorescent flashlight uses this technique. The fluorescent light's a very efficient way to create light from electricity. And incandescent light works by heating a metal to the point where it gives off light. The direct excitation of atoms results in a light with very little heat. And those are the two reasons that fluorescents are always used in large buildings. Oh, you only heard one reason? Well, it's two. The direct conversion to light saves on light per watt, and the absence of heat saves on air conditioning. The unit that's used to measure emitted light is the lumen. A 40-watt fluorescent lamp produces more than 70 lumens per watt, while a 40-watt incandescent only gets up about 12. Because nothing in the fluorescent is burning, so to speak, their life can be as high as 20,000 hours. The reason that incandescents hang on has to do with convenience. It's simple to change the wattage of one. You just replace it with another one. But the fluorescent ballast has to be designed for a specific lamp, so you might change a cool white for a daylight, but they're going to have to be the same wattage tube. Advances in manufacturing have created smaller and smaller power supplies for fluorescent lamps, and you can now get one that screws right into the incandescent socket, ballast and all. Modern science will now have to attend to the final problem of the fluorescent incandescent replacement scheme: how to hold the lampshade.
This is my favorite show. I salute it. Whoops. Too much butter on the darn popcorn.
This is Domtar Fine Papers in St. Catharines, Ontario. You've probably had their product in your hands at one time or another, especially if you own an Ontario driver's license. The term fine paper differentiates paper manufactured here from cardboard and newsprint. As well as the products you see in this display, this plant also makes the paper that we type, photocopy, and write on. The raw material for paper is wood pulp from various species of tree. By the time the pulp arrives here, it's been formed into damp white slabs. The other main ingredient of paper is paper, up to 30% of the total content. The paper industry was a little nervous in the 1970s with the supposed coming of the paperless revolution, but as it turns out, the computer's actually been good for business. This is essentially a big blender. The pulp is being mixed with water to the consistency of loose oatmeal. Recycled paper has to be fed to a separate blender first, and is put across shaking screens of various coarseness to remove paper clips, staples, and other non-paper items. This city block long monster is called, what else? A paper machine. Its operation is simple. Pour in wet fiber and paper comes out the other end, with a few interesting operations in between. This surface is called the wire. These days it's actually a synthetic fabric. The wire section of the machine is an 80-foot long belt that goes around in a big loop. This is the head box. It squirts watery fibers onto the wire. By the time the fiber reaches the head box, it's been refined so that all of the individual fibers are the same length. They've also been nicked slightly so that they'll lock together more readily. The fiber squirting out of the head box is 99.5% water, and the wire is traveling just a tiny bit faster than the flow from the head box. This is a critical adjustment and is responsible for the thickness and strength of the final paper. As soon as the wet fiber hits the wire, it begins losing water. A system of suction boxes and gravity help draw the water away. The final arrangement of fibers is born on this belt, and this system is why paper has two slightly different sides, the wire side and the top side. The edge of the flow is trimmed by a small jet of water. The leftover portion is collected and fed back into the system. By the time it reaches the end of the wire, the fragile mush is still mostly water. A roller at the end of the wire gives a gentle squeeze. Immediately following this squeeze, the paper is still about 80% water. As a testament to how well the fibers interlock, the wet blanket is now strong enough to be removed from the wire and transferred to another belt. The second belt is a felt material. In conjunction with rubber rollers and pressure, the felt removes more water from the paper. This is starch being applied to the surface. This not only makes the paper look and feel nice, it will prevent ink from penetrating too deeply. Depending on the type of paper being made, various coatings might be applied. These rollers are steam-heated dryers. This is the backside of the dryers. This unit constantly monitors the thickness of the moving paper using a small radioactive source, much like a home smoke alarm. Just about every parameter is constantly monitored by a computer, and fine adjustments are made. Imagine the difficulty of getting this machine up and running, with wet mush pouring in at one end and dry paper coming out the other. Paper making is a continuous process, and you can't just stop it when the roll at the end is full. No problem, you just need one of these rigs. If at all possible, the paper machine is never stopped, even when the paper breaks. There's a definite art to rethreading the machine while it's running. At first, this seems like a terrible waste of paper, until you realize that the spoiled paper is simply fed back to the start of the process. Spoiled paper is called broke. Because this plant makes fine papers, the various grades and colors have to be stored until that particular paper is being made again. In lesser grade paper making, this stuff might be just thrown together. This paper machine has an extra roller installed so that it presses against the river of water and fiber on the wire. This is where the term watermark comes from. Most customers order their paper in large rolls for further processing. In the case of French fry bags and soft drink cups, further coatings will be applied by the customer. Other orders are cut and packaged right at the site. The 3 paper machines at the St. Catharines plant turn out over 60,000 tons of paper a year. We'll let you figure out how many sheets that is. In 1979, the last year we have figures for, the 400,000 elevators in the United States and Canada traveled 1.7 billion miles, up and down, and 50 billion people took rides on them. Gee, by my math, that means that some people took more than one trip. A good guess would be that elevators carry more people than other modes of transportation. Elevators of one sort or another have been around since ancient times and undergone a lot of change. For one thing, the slaves have now been largely replaced by electric motors. For another, elevators have become the safest mode of transportation. One insurance company calculates that it's 5 times safer to take an elevator than to walk up or down stairs. Until 1852, most elevators had a serious defect. If the hoist rope broke, the elevator would crash to the bottom of the hoistway. In 1852, Elijah Graves Otis was given the task of building a freight elevator for the company he worked for. Elijah gave some thought to the problem of falling down and came up with this. It was based on a wagon spring. The weight of the elevator platform was enough to place enough tension on the spring to keep it pulled in. If the hoist rope snapped, the tension on the center of the spring would be lost and the ends would jam into the ratchet bars along the side of the hoistway, stopping the descent of the platform instantly. This is a picture of Mr. Otis demonstrating his device at the Crystal Palace in New York. He had himself and some freight hauled up in the air. Once he was up in the air, for everybody to see, he ordered the rope cut. The safety worked. Over the gasps and applause of the audience, Elijah Otis bowed and said, "All safe, gentlemen, all safe." Modern elevator safeties all rely on some sort of centrifugal governor. A separate rope attached to the elevator spins the governor. If the preset speed is exceeded, the governor first removes all power from the drive unit. If that doesn't stop the car, the governor clamps on the safety rope, giving it a tug. That tug trips the car's safety brakes. There are several different arrangements of this, but they share the benefit of being passive. They don't require external power of any kind and will function even in a power failure. Safety is sort of intrinsic to all modern elevator designs. Some elevators that only travel a few floors are hydraulic. They operate like the lift in an automotive garage. Nothing life-threatening can happen here. Your basic high-rise hoistway gives a little more food for thought. The variety of elevator drives from the beginning of the century have mostly given way to the traction drive. The traction drive relies on a counterweight. The counterweight's set to be about 40% heavier than the empty elevator. Under average loads, they'll be approximately the same weight. The counterweight and elevator are connected by several independent ropes that loop around a large drum with grooves, called a sheave. The elevator motor drives the sheave either directly or through a gearbox. The weight of the elevator and counterweight on the sheave provides traction. If either the counterweight or the car were to touch the bottom of the shaft for any reason, weight on the sheave would be lost, along with the traction that the weight provides. The ropes are steel cables, although elevator people still refer to them as ropes. Any one of the several ropes would support the elevator all by itself. Elevator ropes are different from ordinary steel cables in that their individual strands are all twisted in the same direction. This gives the rope more traction. Even in the unlikely event of a complete failure of all the ropes or the traction device, there's still a separate governor-operated safety braking system attached to the car. If something goes wrong to send the car to the bottom of the shaft at normal speed, the governor won't trip, but that's been covered too, with a big spring or hydraulic bumper called a buffer. Each car is also equipped with a load-weighing device. The load-weighing device is used for safety, but also to aid the control equipment in the matter of acceleration and braking at the various floors. Older elevator control equipment used a miniature model of the elevator system with microswitches to control stopping, starting, and leveling. Nowadays, no moving parts technology has replaced this in the form of magnetic sensors and computer control. Computerized group controllers manage large groups of elevators, parking specific cars in designated zones, sensing which cars are full of people already and which ones have room in them to make a stop. They even change the battle plan depending on whether it's up rush hour or down rush hour. The mechanism that operates the doors on the car also unlocks and operates the doors on the individual floors. This ensures that the doors to the shaft can't open unless there's an elevator behind them. An extra bunch of controls allows the doors to begin opening just as the elevator's coming to a stop. Elijah Graves Otis didn't live to see all of this. He died shortly before the American Civil War. His sons did develop the business further. Among Otis's contributions to vertical transportation is this simple-looking button. It's the one that doesn't move at all when you touch it. Now, most people will tell you that this button senses the heat of your finger. Well, how come you can trip it by touching it with a car key then? Acme would like to settle this matter once and for all. The plastic center of the button is conductive, and behind each button sits this little neon tube. The electric potentials on the tube are set up so that the neon's just ready to ionize. Touching the conductive plastic provides a ground return that trips the neon into ionizing. If you've ever started a fluorescent tube by brushing your hand along it, you've experimented with this effect. We don't have the proper electronics set up here. In the proper setup, once the tube fires, it latches on and keeps glowing. The orange glow from the tube is what illuminates the plastic bezel. The sensitivity on these is set so that even a gloved finger will trip it. There is a solid state replacement for this nowadays, and it doesn't use heat either. Next time you're in an elevator and someone's saying the buttons use heat, you can correct them now. Tell them where you learned this. Have them send me $1. Today, elevators travel at speeds of up to 1,800 feet per minute in hoistways serving up to 110 floors. The development of the safe, fast passenger elevator allowed the development of tall buildings. Today, the Otis company is very large, but every time I cross the threshold of an elevator with his name cast in it, I like to think of Elijah with his top hat, beard, and wagon spring. All safe, gentlemen. All safe.